Hi, welcome to our video on tuning accuracy and precision of biosensors. So at Zimmer & Peacock, we're often asked the question, what is the accuracy of your biosensor? In that case, what's the accuracy of your ZP biosensor? And obviously at Zimmer & Peacock, we have a whole list of biosensors from glucose to lactate, sodium, potassium, to purines, to fructose, to cortisol, to pH, calcium. There's a whole list of them, ammonium, pH. So what we're going to do here is talk about what is the accuracy of our biosensors. And so the answer to it is, what is your application? And now I'm going to explain why the answer is, what is your application? Because when people ask the question, what is the accuracy of a biosensor, they're really imagining something like a temperature sensor or a pressure sensor or a gyroscope. Those kind of sensors are relatively isolated from the sample itself. And what I mean by that is the sensor is not in the sample. It's not in intimate contact with the sensor, with the sample. So a temperature sensor, will be somewhat shielded behind some membranes or even a metal or plastic. A pressure sensor is also shielded from the sample itself. But when you look at biosensing applications, you're often going to find that sensor is in intimate contact with the sample itself. So, for example, here's one of ZP's biosensors, and in this application, it's in a drop of blood. Now, the signal that will come from that sensor is both a function of the analyte of interest. It could be glucose, oxygen, cortisol, pH, etc. But the signal is also proportional to the sample type. So here we've got another ZP biosensor. This is a chili one. And here the sample is a chili sauce. And so if you were measuring something in blood or measuring the same thing in chili sauce, you're going to end up with essentially different results. And so you actually need to have different calibrations and different routines depending on the sample type. So when we talk about samples and matrices, the kind of things that we do measure analytes in at ZP are blood for definite, urine, saliva, nasal swabs, sweat, interstitial fluid, breath, vapor, gases, and foods, for example, chili sauce. So when answering the question, what is the accuracy of your biosensor, we do have to come back and ask you, what's your application? What are you actually trying to measure it in? Because it's not the same as a temperature sensor where you can sort of characterize temperature sensors, and how they perform is somewhat independent of the sample itself. So if you were measuring temperature in cheese or temperature in water or temperature in the air, the temperature sensor is going to behave the same way, but it's not the same for a biosensor. Now, what people are asking us obviously is, essentially they're expecting that, that our accuracy and precision is good, that our sensors are accurate in terms of they're telling the truth and that they're precise. Now, the situation can be, as you go from matrix to matrix, you can be precise, but you're not necessarily accurate. And that's really the matrix effect. We call that, an offset essentially. And that needs to be characterized. And and these offsets or these matrix effects or these sample effects, there can be interferences. In the case of glucose sensors, it could be acetaminophen and ascorbic acid. There can be sensitivity changes. There's things like hematocrit effect or number of red blood cells that can change sensitivity. And you have these offsets. Offset could just come from a simple pH difference, let's say. So if we take a simple case like a glucose sensor, here we have a glucose sensor with a drop of blood in it. So the signal there is proportional to glucose. But also, the signal is affected by the hematocrit. And now the hematocrit is really the volume that's taken up by red blood cells. So if we just illustrate that a bit more, if you centrifuge whole blood, you're going to find a dark red phase at the bottom of the tube and a sort of clearer yellowy phase at the top of the tube. And at the top we basically have plasma, and at the bottom we have red blood cells. Now in this case, the red blood cell volume is about 42% of the entire volume, and the rest of it is 58% of it is plasma. So there we would say the hematocrit is 42%. So what we're saying is, when asking what the accuracy of a biosensor is, we do have to come back and ask the question, what are you trying to measure? What is the application? Because depending on that, there'll be different interferences and different things to consider. So for example, if we consider hematocrit and we consider hematocrit on glucose, you can measure several glucose concentrations, be it sort of 50 mg per dl up to something like 400 mg per dl. Now, if the hematocrit is 70%, we will have one sort of sensitivity. If the hematocrit is 43%, we'll have a different sensitivity. And if the hematocrit is 9%, we're going to have a different sensitivity again. So our accuracy is, we have to basically have different protocols for each type of matrix or each type of sample, and that's why we have to ask the question back, what are you trying to measure? Now, at ZP, we do have basically a technology stack that will help you tune a biosensor to your application. So, for example, you could take a ZP pH sensor or a ZP glucose sensor. You'll take one of our off-the-shelf meters, and this is really just for tuning the sensor to your particular application. Now, at this point, you'll put, for example, a drop of blood on there or some urine. So in the case of pH, you could be measuring pH in the urine. In the case of blood, you could be measuring glucose in the blood. Now, what you'll do is you have a sample which you're testing on our sensor, which is plugged into one of our meters. Now, at the same time, you can test that sample on it doesn't have to be a big clinical analyzer like this, but what we're seeking is we're seeking the truth, we're seeking the reference value. You take that sample, you test it on in the case of a medical diagnostics, you test it on an instrument that's kind of FDA approved, probably normally resides in a central laboratory or hospital, and you test the sample there. Now, a blood gas analyzer like the one I've shown in the image will actually give you back over 10 results on that blood. Now, in the case of glucose, for example, it will give you the glucose reading. So that's good. So we essentially know the truth through the reference measurement. Now, what we next do then is we have an app that runs on the Android. And what that app does is it runs a method file which tells essentially tells the meter what to do. So if it's a glucose sensor, it'll give it one method file. If it's a pH sensor, it'll give it another method file. But we run a method, and the meter through Bluetooth connection gives the data back to the app, and we hit upload. Now at this point, our cloud technology kicks in, because the data, as long as we've got a connection to the internet, will go to our Djuli database. So Djuli is a ZP proprietary database for the saving, the analysis, and the sharing of data. Now, what that allows us to do is it allows us to read the raw signal for different samples, and the signal should be proportional to the concentration of the analyte. So in the case of pH, we'll have a signal that's proportional to pH. In the case of glucose, we'll have a signal that's proportional to glucose. In the case of lactate, we'll have a signal that's proportional to lactate, for example. And ZP has over 20 of these off-the-shelf sensors. Now, the next thing that happens is we want to make our biosensor that we're trying to tune at this point to the application of interest. We're trying to make that correlate one-to-one with the clinical sample or the reference value. So what we do is we have raw signal from the ZP biosensor, and we have reference values. So if we just use glucose as an example, we can have a series of reference glucose values, and we will have the corresponding ZP sensor value. Now, we want them to be one-to-one. Now, if they're not one-to-one, then what Djuli will do is Djuli will basically the AI algorithm will re-examine the raw data and it will come up with a better calibration from the raw data to try and improve the correlation between the reference value and the biosensor value, and it will keep on iterating. We'll do an extraction and re-looking at the data until we get a sort of closer to a one-to-one correlation, at which point the Djuli database will stop. So in summary, we are asked, what is the accuracy of your biosensor? And the answer is, what is your application? And the reason it comes back like that is because unlike normal condition type sensing, vibration sensing or pressure sensing or temperature sensing or movement sensing, our sensors are in those samples, be it food or be it oil or be it human blood or be it urine. Our sensors are in there, so they do have to be tuned for each particular application. And so this ZP accelerator platform is the best way of taking an off-the-shelf ZP sensor, exposing it to the sample or the sample of interest, and then using a reference value, we're able to then iterate the data extraction until we get the best correlation with the reference. Now, if you have any questions regarding Zimmer and Peacock, then I wouldn't basically don't hesitate to contact us on this. So in summary, what's the accuracy of the sensor? The answer is what is your application? And the second answer to this is, let's run it through the Djuli accelerator and we'll see if we can tune the sensor up to give you good accuracy in your particular application. And if you have any questions, don't hesitate to contact us at Zimmer and Peacock. Okay, thanks very much.